going to hand out your quizzes before the end of class, so help me remember that that's what I have to do. I think I have better check and make sure that I have those grades recorded. We are going to talk today about section 2.3, which is over graphical misrepresentations. Okay, and it is just a really short lesson, so you'll probably get a little bit of it from the reading. I'm going to highlight a couple of things that I want you to look for as you're reading, all right? Some of the things that we would look for in those graphical misrepresentations. And then we're going to move on and start on chapter 3, which for today is going to be the measures of central tendency. So what I'm going to start with is that 2.3 graphical misrepresentations. And what I have here are two graphs, okay? And there's lots of different ways that we can inform using a picture. And there are a lot of ways that we can mislead, which would be unintentional, or deceive, which would be intentional, with our graphs, all right? And notice here, just compare the two graphs that we're looking at here. They are both about life expectancy. I don't think you can see the scale on the bottom very well, but that's talking about the life expectancy. So it's a time plot from the year 1950 through 2010, all right? 1950 to 2010. Can somebody explain to me what differences you see there between those two graphs? They're both graphing the exact same information.
The first one has like a really steep slope, with the other one's like almost.
Okay, so in the first one, if I only put up the picture of the first graph, if you were reading an article, let's say a news article or something like that, and it was talking about the life expectancy since 1950, you would infer, I would assume, from that graph that, man, our life expectancy has just really skyrocketed, right? We are living longer. We're doing so much better. All right. Look at the other graph, though. Just like we were talking about, Michael was talking about. What do you notice there? It was, I liked your word. What did you say? It's the second graph is almost what?
It's almost flat.
It's almost flat, right? There is still an increase, right? There is still an increase in life expectancy, but it's not nearly as dramatic as this image over here, right? Can you tell at all what the difference is?
Starting point.
Yes, the starting point, right? So in the leftmost graph over here, we have a starting point of 0. All right, so we're going all the way from 0 to age 80, correct? Over here, it's like we zoomed in and we're focusing on the ages between, I think it says 68 to 78 are the numbers on the scale on the left-hand side, the vertical scale over there. So it's like we zoomed in on this one section of age ranges. Now that age range was increasing, right? But if we're looking at the overall picture, you can see how when you don't start your scale at 0, then it's harder for us to be able to look at it, right? It's harder for us to interpret and make an assumption or make a judgment based on that, okay? Let's look at another one. So I have two bar graphs here. The one on the left is talking about the burglaries from in 2009. And then, of course, the one over here is talking about burglaries in 2009 in the US. They're both graphing, graphing the same information in essence. Somebody tell me what the difference is between them.
The bin size.
Do what?
The bin size.
The bin size?
One's going
Yeah, I can see. Do what?
Horizontal and
horizontal versus vertical. That is obviously the difference here, but that doesn't mean that one graph would be more misleading than the other. I don't like to, I'm so conditioned to see vertical graphs, right? To see vertical bars. It's harder for me to see horizontal bars, but that doesn't mean that they aren't valid.
Going back to bin size, the bins are
The bins are not even,
like,
and how is that? How are they not even?
One's covering all the months, and then one has July, August, and then it says other months.
So
Okay,
one has
right?
two
The
months and
first
the other
one
one
is
has
like
the other.
a generalized overview of the year, and then the second one, it actually breaks it down.
All right, so
It's
over
a-
here, we have, on the leftmost graph, we have each individual month, right? And then on the right, on the left-hand side, we have July and August, right? We're focusing on July and August, which are summer months, right? Summer months. And then you have all the other months. What normally happens in the summer? What do people do in the summer?
Vacation.
They take vacations, right? So you're away from your home. And nowadays, people post all over social media that they're on vacation, right? So it's very easy for people to know that you're not at home anymore if you're doing it live, okay? So it would make sense then for you to have an increase in burglaries, you would assume, comparatively to the others. But if you want to just know the overall burglary rate for the year 2009, you need to look at all the months and compare them to each other, right? So if we're looking here at just the bar graph with each individual month shown, I can still see that July and August are the highest months for burglary, but they're not almost twice as high, right? Because isn't that what this leftmost graph is indicating? If you're looking at the length of the bar for the top one versus the length of the bar for the bottom one, right? The July, August data is almost twice as high as the others, right? That's what that bar is indicating.
Yeah, at first glance, it's almost like, okay, well, this is every single month is this, and this is just these, so it looks like it's double, when really, if you divide it in half, it's most of the same.
It's not, yeah, it's not dramatically larger. So you can see how this is done, right? Interesting. You want to look at those things. How about this one right here? This right here is just two different ways for us to be able to represent the data that we're looking at, right? On the leftmost graph over there, on the bar graph, I'm going to call it, we have the SAT scores, okay, for math. And then on the right, which is again our time plot, we are talking about the individual data points. So in other words, when you're doing a time plot, this point right here represents the average SAT score for the year 1991. And then we keep moving on. So each of those data points is the average score for that year. And they're just kind of connecting it. Now, in this one, there's nothing wrong with either of these two graphical representations. It's just one may be more appropriate than the other, depending on what you're looking at. Typically, we would say that if you're kind of looking for a trend, okay, if we're looking for a trend, we typically see this time plot line, or sometimes it's called a trend line, so that I can kind of see what's happening over time, okay? We might look at a bar graph like this if I want to maybe compare, right? Didn't we say bar graphs were for comparing things to each other? Might be more appropriate if I wanted to compare, you know, years to each other, as opposed to a trend that might be happening over time. So in this example right here, we are not necessarily looking at one being misleading. We're more looking at, well, which one would maybe be more appropriate, okay? Okay, speaking of, well, I'll put that up there in just a second. Now, this is another one that I think is kind of fun. Pictures, right? Here's our bar graphs. Here's our pie charts. So both of these pie charts are graphing the exact same information. Can we see that? Right, their percentages are exactly the same. What would make this misleading?
3D almost looks like there's missing information, because there's
Okay, because it maybe
empty
looks like
slots
there's gaps. What else? The 3D one's fun, right? Isn't it cool that we can make graphs now that are 3D? Heck, Excel does it pretty easily. I think Google Sheets does it now. I think that's pretty awesome. Why would that not be the best way to represent our data? If I'm looking at the understanding of gas prices right there, according to the left graph, which is 3D, it almost implies that the taxes, which are 32% right there, that looks like the biggest chunk, doesn't it? Pictorially. Okay, even though we know we can say that the number 32 is obviously less than the number 48. The thing that you get with 3D graphs is you'll have this extra lip here, right, to give dimension to it. And our eye interprets that as having more surface to it, like more in it, so to speak, right? And so that's why 3D graphs are typically not used. That's one of the reasons why they're not used. If I come over here and look at this graph here, I can get the same information out of this rightmost pie chart, okay, as I can the pretty 3D one over there. And I'm not fighting with making my brain, you know, logically, I'm not fighting with that spatial additive to it, if that makes sense. Does that make sense to y'all? Yeah? Okay, because 3D ones can be a little bit misleading. Here's another one here. There's another idea about pictorial graphs, where we let pictures or symbols represent our graph instead of straight on bar graphs, okay? This is implying that we have a whole lot going on right here, and then each of these are representing. It's hard for me to be able to compare these things, right? I have 4.3 and 4.1 billion here, but I can't really compare this 4 billion to 40 billion, which is what we would have here, right? It's just a very hard way for us to understand the information that's being given. When you're doing a graph to represent the data that we're talking about, the overall impact you want to make with the graph is to convey the information that you have found. And sometimes, even though it looks cool, sometimes we can end up muddying that, right? We're not exactly conveying the information that we want, all right, as easily as we would want it to be. Okay, all right. So overall, I would say this. There's 3 things I would like for you to take away from this. When we're thinking about graphs, right? We can have graphs that mislead. When we think of misleading graphs, that means that it's kind of unintentional, right? I didn't mean to purposely, I didn't mean to do that. I chose a graph I thought would be representative, but it was misleading. It unintentionally creates an incorrect impression. As opposed to deceiving, now there's, think about the English language, right? If I am deceiving you intentionally, that is an intentional thing. And I am purposely creating an incorrect impression. One I want to pull up for y'all in just a second after you write this down has to address this idea of scale. So when we think about our graphs, one of the things that we can mistakenly do to misrepresent has to do with the scale of our graph. Scale of our graph, an inconsistent scale, so we don't have consistent values, right, between our scales. and then misplacing the origin like we saw above. And then finally, we want to talk about those bars. This is why we make our bar graphs to have uniform size, because our eyes compare area. Spatial awareness. And when we don't have things that are equal, we put more weight into it inadvertently. Okay, do we have that copied down? It's kind of the highlights from section 2.3. You have some short, I think it's a short lesson on 2.3. That kind of walks you through that. Now, I wanted to take you here. I can't remember. I think I mentioned this last week. But I want to show this to you anyway. So this is, obviously you can see me pulling up. This is the COVID dashboard from the state of Texas. What I want to look at are fatalities, right? We talked about this last week, didn't we? When we talked about the shape of our distribution, right? This is a histogram representing the data for the people who died from COVID based on age ranges. And if you look down here, right, I have less than 1 year, but starting after that, I've got 1 to 9, 10 to 19-year-olds, 20 to 29. Each of these are divided up until you get to age 59. We are talking about bands of 10. Now, all of a sudden, we go now to every 5 years for the 60s to 70s. Every 5 years. What would this graph look like then? Because to me, that's misrepresentative, right? That's a misleading graph because our scale is not the same. They didn't group it the same way. They didn't bin it the same way, did they? If I took the 65 to 69-year-olds now and I combined it with the previous, the lower half of that age range, right? I've got 13,000, we'll call it 13,000 deaths, right? I would have, let's just take that bar right there and stick it on top, right? And then I would have over here these 70 to 79-year-olds, right? There's 14,000 of them. That would be a bar up here. I just wonder, why would you not, right? Statistics, right? We're trying to convey this information. And I just, when I saw that, I was like, oh, please, why are we doing that? And then
they make the last one look really drastic when it starts at the 60, like the 60 to 65.
I know this is just one of those times. And all I just want to point out is when we have math that's used in the real world, sometimes if we don't understand it ourselves, it's easy to go along with what we're looking at, right? It's easy to see it because we don't know if it should be any different. I'm just saying that if we're talking about graphical misrepresentations, this to me would be an example, and there's plenty of other examples you can find in the news of graphical misrepresentations, whether they are intentional or whether they're just, what was the other? Unintentional, right? Whether it's just a I don't know.
It's really curious why they would do that, because it almost seems like it's to make it look less scary for someone under 80, when you would think that they would want it to look, more scary with, but, instead of a steady incline, it's just like, oh, it's not that bad, and then when you hit 80.
So just look, when you're looking at information that is given, just be sure that you are looking at all of the information that's being given, right? Because you're going to know by the end of this. I'll never forget, I went to a conference for teachers, and they had a lesson that we were listening to, an author, a statistics lady, and she was saying that and I did not realize this, that doctors' boards, and I guess, in the medical profession, part of their probably continuing education, I would think, they will have statisticians come and do a professional development day for them, so the doctor understands and can interpret the statistics, which I thought was interesting. So, y'all are learning, right? You're learning the basics of statistics, right? And you're going to look for things that could be either intentional or unintentional, but still would be misleading, right? In things like that, just like the numbers, right? When we compare things, we want to look at things that are proportional to other and not simply straight across numbers. Okay. Just because we have a histogram up here, again, they've done the same thing with the data for the 60 to 80 years. So I'm not really sure. I mean, we can stack those on each other. If you were to describe this data, right? Remember, we have 4 ways to be able to describe our data: uniform, normal or bell, skewed left, and skewed right. Let's pretend that this is not misleading. Let's just look at the shape. What would you say here? I'm up for, it's very subjective. Well, it's not very, but I would say there's 2 graphs that you could probably convince me of. Which descriptions do you want to have on this?
Almost a bell.
Almost a normal shape. And why do you say that? I would agree.
Just because it's got the low and the high.
I would say that you've got the tails over here. Your peak is somewhat in the middle. There's probably an argument if anybody wanted to say that this was maybe skewed right. Okay, it could probably be that as well.
There was one on the homework that I want to say it looked close to that, and I got it wrong at first, and it was a bell, and I was like, what? Because I kind of thought it needed to be.
It does have to have the 2 tails, but they don't have to be even, so to speak. Typically, you're trying to see, where does the middle lie? If the middle of our bell, let's say that the middle of our bell lies in between the 30 to 39-year-olds and the 40 to 49-year-olds right there. Something like that looks to me like it could be somewhat shifted to the left. So if our major peak is shifted to the left of the center, then it would be considered skewed right. Again, that would be somewhat subjective.
And the one tail wouldn't be as long if they actually represented data correctly.
Yes, I would agree. You would have it would look different over here, but we're pretending that it was not. We're just talking about the shape. Okay, so I think that's kind of a fun example, if you will. Now, moving on to summarizing our. So now we're going to talk about chapter 3. Okay, so chapter 2 was that graphical display or using tables, right? Chapter 2 is about some sort of displaying of the data, whether that is summarizing it into a table or whether that is showing that display in a graph. Remember that the graph is the pictorial representation of our table of data, right? And that's chapter 2. Real quick, as we're kind of refreshing our memory on this, when we think about bar graphs and pie charts, what type of data do we use to represent pie graphs and pie charts and bar graphs? We only have 2 types of data that we're talking about: quantitative or categorical? Of those two choices, which of those two variables is used to is represented by bar graphs and pie charts? Do what? That's all right. We're guessing, right? Okay, so quantitative is only histograms, right? Histograms. Dot plots, right? That was the other one we did. Okay. And that's because, think about our histogram we just looked about off of the COVID numbers, right? We're going to take, we have all sorts of numbers for age ranges. We're not going to plot all of them individually. We're going to group them into categories, for lack of a better term. Qualitative or categorical data is what we use for pie charts and bar graphs. Okay, I think y'all need to practice. How many of y'all practiced with that Desmos vocabulary thing that I put up at the beginning of the semester? Okay, some of you may have, some of you didn't. You might need to go back in and practice those terminologies, right? It was kind of apparent on the quizzes that I gave. Okay, you've got to get the vocabulary down. Okay, so once we move past being able to graphically display this information, now we're going to talk about, well, we have some measures. How do I quantify the middle, right? How do I quantify the average? Well, we have the mean, the median, and the mode. Mean, median, and mode. You've been practicing these things since probably the 6th grade, as soon as you learn how to do adding and division, okay? The mean is our average, okay? We've always called it the average, but it's in statistics, it's termed the mean. We have the median, which would be considered the middle. And then we have the mode, which would be considered, which is what we think of when we talk about something that's used most often. Now, remember how I talked the other day and I mentioned that, what did little n, the variable little n, stand for? The sample size, right? The sample size, the number of data in our sample. Little n is the sample size. What does capital N stand for? The size of the population. That's correct. Now remember, I also told you that we're going to be growing this list of variables, and I have 2 of them sitting up here. You better write down. Students always forget this. When we talk about the average or the mean, I can talk about the mean of the population. So I can find the mean of the population. It doesn't happen very often because in order to find the mean, I would have to have all the numbers. But I still can have the population mean, or I could have the sample mean. So what we have up here is the symbol that we use to represent the population mean looks like this cursive U. It's a Greek lowercase letter. Looks like a cursive U with a tail in the front, and it's called mu. The sample mean is exactly what it appears to look like. It's called X bar. So X bar represents our sample mean. Mu represents the population mean. Okay, you'll start to learn that all the Greek letters represent the population. Okay, and we'll have other variables that are representing the sample. Now, somebody tell me, how do I find the average? Mathematically, how do I find the average? Add them all up and divide by the total number, right? That's exactly right. We add it up and divide by the total number. Now, what do I do that's special about a median? How do I find the median?
Put the numbers in order from least to greatest and middle number.
Okay, so the median would be the middle number, and you're right, we have to order the list. First, you have to put the list in order. Typically, we go from least to greatest, and then if I were to fold the list in half, The middle value is the median, okay? And then the mode would be the thing that we use most often. Is there always going to be a mode? No, there's not always going to be a mode. There will always be a mean and a median. Okay? Now, let me go here. All right. So here I have some data for the salary for the Tampa Bay football team from last year. Okay, so I think they were the one who won the Super Bowl last year, if I'm not mistaken. All right, and so this was the salary for them, you know, for that starting season. Okay, and this it can be found on the internet. It's really kind of a cool place to go to. But I have their base salary, which is what we're going to focus on because I don't know anything else about the rest of that stuff. Okay, base salary. Okay, and what I have here is all of the base salary. So if I scroll down here for the 53 people that I assume are on their roster. Okay, now who is at the top of that list? What name do you see there? Tom Brady, right? Who can tell me about Tom Brady? He's what? The most paid. I think he is. He's really high paid, right? Yes? Okay. So, and since we're in StatCrunch, it's hard to see what that number is right there without commas in it because there's so many zeros, right? Okay, so this is one. So it looks to me like he has a base salary of $15 million. Okay, $15 million. And then you can see in there that there's some other people that have a bunch of money right there too, right? Put the comments in there. I don't know all these football players. I just know Tom Brady, Gronkowski, I know here. All right, now if I wanted to find out what the average salary was for this roster from 2021, what would I do again?
Add all their salaries together and divide by the.
Okay, so I'm going to take everybody's salary, add it together, and divide by the total number of players, right? All right, so it's a pretty long list. I don't really want to do that. Instead, I'm going to calculate this from StatCrunch. Now, be aware, when I give you this information on a test, I am going to ask that you hand calculate a small list, and we're going to practice that in a minute. I'm only going to ask you to do that on a list that would be, 10 or less, right? Anything over that, it's a little cumbersome. We let technology do it. But this information that I'm looking for, the mean, the median, the mode, all of those things are what we call summary statistics, right? It's a statistic about the data that I'm looking at. So I'm going to go to summary stats and I choose that I'm looking at a column. So here I choose the base salary. That's the one I want to perform this information on. And remember the other day when I was getting fancy and told you about all the commands that you can choose for the computer? Down here in the statistics box, everything in it is gray. I don't want all of those information. All I want to focus on are the mean, the median, and the mode, right? Because that's all I'm looking at right now. So I'm going to click on mean, and then I'm going to scroll down here. And I'm going to hold the control button down, and I'm going to click on median. And then I'm going to scroll down to the end of it. And I'm going to click on mode. So I put the three choices that I made over in the right-hand side, and I'm going to come in here and I can look at their data, their summary statistics. Okay. So what this says is that for the players that year, we had an average salary of, what would that be, 2.6 million? $2,600,000 $641,632, right? So 2.6 million is easier to say right now. Okay, that's the mean. The median, however, was what? 900,000 or 0.9 million, if we wanted to compare the two. Okay. So what we're looking at here is an average for the football players of 2.6, that is at 2.6 million versus the median of 0.9. Leave it at that. All right, now let's pretend that you're a Baylor football player, right? Or you know a Baylor football player who just got recruited from Tampa Bay. And he's psyched about it, right? He's like, all right, I'm coming out of college. I'm going to go work for Tampa Bay. I'm doing a little due diligence and I'm going to go see what's the starting salary or what is the average salary then for the Tampa Bay information, right? For the Tampa Bay. So he sees that the average salary is 2.6, right? That's what he looks up. Average salary is 2.6. He goes away, goes home, tells mom, we struck it rich. I'm going to make $2.6 million because that's the average salary that they're paying at Tampa Bay. How is he wrong?
Because their top players are paid like considerably more than.
And what effect does that have on the average? Why does it make the average higher? That's exactly right.
It contributes more money to that total.
Okay, so remember that when we take an average, we have to add everybody's values in there. So people that have more, right, they're contributing more to that sum, right, to that overall sum. And so they tend to weight it more heavily in that direction, all right? It tends to pull the average over towards that, okay? So yes, that's exactly right. The more appropriate method for determining what you could expect for a salary if you're going in is something around the median. Now remember, how do we find the median? Monica, how do we find the median?
You put the numbers in order,
And
the middle number.
it's the middle number, right? Whatever that middle number is means half the players make more than that money, half the players make less than that money. The median is simply the middle of a list. Again, if I was to order that list and fold it in half, the crease where that would be at is going to just be the crease, right? That number does not change. The median does not change. The middle of our list is not going to change. And so remember that when we're thinking about the middle, again, half the players are going to make salaries more than 900,000, right? And half the people are going to make less than 900,000. Okay. Typically, when you have data that would be skewed, okay, you want to use the median to understand is a better indicator of what the data is looking like because of this. Now, we can see that the mean, median, and mode can be calculated here. I do want to point out what this looks like graphically, going back to chapter 2. So again, this is quantitative data, right? This is the salary that they're making. That would be considered quantitative data. Everybody's making different values. Okay, there's an infinite number of values, let's say. So I'm going to do a histogram. I'm going to do a relative frequency. And here is the graphical display of that data. Remember that the histogram is supposed to give us a sense of what does that data tell us, right? If we only look at that column of data, I don't really know much about it. I can quickly graph it and I can go, oh, okay, so this is skewed, right? All right, and we can see that, remember the tall bars represent where a lot of the data is at, right? And the shorter bars represent less data in them, okay? And so if we're looking at this, what did we say? The median was 900,000. This bar is representing 0.75 up to
2,500,000.
All right, 2,500,000. So let's do this. Because it'll be easier to see. There. All right, now what did I do here? So what I did is oh. Hide it a minute. Oh. No. So what I did here is I asked us to add the median. Where in this graph is the median falling? And where in this graph is the mean falling? Right? So if we just think about where the median is falling, which is just slightly to the left of the middle of that tall bar right there, right? Then we can see that half of the players on this team are here just to the left of that bar, right? Half of the players are there. And then the other half represent this value over here, right? You can also see that when we're looking at histograms and our mean and our median don't line up, right? Where is the mean falling? Towards what? The mean that represents that green line, and it is closer to the tail than the median is, correct? What shape did we say that this was? It's skewed right, correct. When we have a skewed right histogram, the mean is moving more towards the tail, okay? Because of those outrageously high football salaries, right? Because of those people that have the $15 million contracts, right? They're pulling the average closer to the tail. And it's vice versa if you have something that's skewed left, right? Skewed left would be pulling the average closer to the left-hand side. The smaller data is what that would be, all right? So when we have data that is skewed like that, okay, and this is where I was telling you, remember how last week we were looking at those histograms, and sometimes they got a little bit, maybe they could go one way or the other. Well, one of the ways to be able to support your conclusion for maybe skewed versus normal would be to calculate the mean and the median, right? If the mean is greater than or less than the median, you have skewed data, right? If the mean and the median are equal, then that's going to mean, I'll just take it down here, this is on the back of your paper, but if you've got data that is, if you have a distribution that is normal, then what we have happening would be the mean and the median are equal. Now, again, this is just this is the perfect math world that you would want it equal. They might not be exactly equal, but you don't have the big disparity, the difference like we do on our football example, right? Here we have the mean, I believe, of our football example was 2.6 million. That's a long ways away from 900,000, isn't it? That's a big difference between those two numbers. Okay, so it makes sense then for us to have skewed data. And again, the average is this thing, this numerical value that gets easily influenced by very large numbers or very small numbers. As a matter of fact, remember I told you that housing prices are typically skewed right, correct? Remember I said housing prices are typically skewed right. So if they're typically skewed right, we would want to look at the median the median housing price for the McLennan County to know what you would expect to pay for a house. Because 50% of the houses are gonna be up to the middle and 50% are gonna be more than the middle, all right? When housing markets are skewed like that, you have those mansions that could pull the average over and skew your data. Okay, so when we think of this, we want to consider the what is resistant. All right. So is the mean, just to reinforce this before we practice, is the mean, I'll just say it this way, the mean is very influenced by outside numbers, right? Very influenced by large or small values. The median is what we call resistant to those outliers, we'll call them, okay? The median is resistant, the mean is not. And that's going to be a theme that we're going to see as we move through a bunch of this moving forward. Okay, let's practice. So on your paper there, I gave you the data list that we're looking at. Okay, I have the same data list up here. So there's a group of BYU students who collected the data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed limit was 25. And I want you, on your paper there, to compute the mean, the median, and the most. All right, so you all do that for me. And we'll go over those answers. This is an example of what I would ask you to do by hand on a test for me, okay? While y'all are doing that, I'm going to call roll 3. Noelle? Here. Madison? Here. Caden? Addison? Michael? Here. Michael? Alicia? Lorena? Here. Monica? Here. Erica P? Here. Jonathan?
Here.
Alexia? Abigail? Here. Erica Smith? Michaela Stroud? Here. Daniela? Here. Julianne? Maggie? Lisbeth? Kayla, yeah. All right, have you got the, the mean? Yeah? All right, how did you go about computing the mean? When you added them up, what did you get?
32.
450?
Yeah.
All right, so what symbol am I going to use, by the way? What symbol will I use to represent the mean here? I have two choices. X bar or mu.
Mean.
Nope. I'm gonna use X bar because this is a sample of 14, right? This doesn't represent the population of speed, right? This is a sample of 14. So X bar is gonna be equal to, and we said, Michael, you said 450, is that right?
Yeah.
All right, and then somebody else told me that the average speed was 32.1. Is that correct? Do we agree with that? Miles per hour. Okay, so that's the average speed. Now, how do I find the median? The median, by the way, is represented by a capital M. That's nothing fancy, just a capital M. Tell me again how I found this.
Right in the middle of the ordered list.
So it was already ordered, wasn't it? Yeah, I already gave you a list that was ordered. If it wasn't ordered, you would have to order it from smallest to largest. And this is an even list, isn't it? So I'm going to find the middle values, which is occurring here at 32 and 33, right? Okay, and I would find the middle between 32 and 33. So that's going to be 32 plus 33 divided by 2, or we all know this, but that would be 32.5, okay? But that's how you calculate it mathematically for numbers that you don't know, right? You find the middle and you add those two numbers together. This is on an even list, right? On an odd list, you're gonna have a middle. You're gonna have the one number that is in the middle. With an even list, I have to calculate the middle of the list. So 32.5. What was the mode? There's no symbol for mode, just
40.
Was that 40 because it was twice?
yes. It would be 40 because it's twice. And there doesn't have to be a mode. Okay. Now, what would you say? Looking at the mean, which is 32.1, and the median, which is 32.5, can somebody tell me before I go graph it, what type of shape would we expect this histogram to look like? What would I expect the distribution to look like? Why? Because the median and the mean are pretty much equal. All right, again, this is real world data, right? So they're not going to be dead on data, exact, but we would expect this picture, this graph, this histogram to be normally distributed because the mean and the median are pretty much equal here. So if I come over here and I graph that histogram, we'll just put those markers up there. Right? I have something that is somewhat symmetrical, right? Okay. Looks kind of funny, but it is up there. It is the value of that. Okay, so being able to, without giving you, oh, I know why. What was that smallest speed? 20? Yeah. That looks better, doesn't it? See how the shape can kind of change if we change those bin sizes a little bit, but change the bin size to be a little, to help us identify that shape. Remember, that's what the graph is supposed to show us, right? It's supposed to talk to us about the data. So if I give you now, or I describe to you a normal distribution, you need to be able to tell me back the relationship between the mean and the median. if I gave you a skewed graph, you need to be able to tell me the relationship between the mean and the median. All right. So when we're looking at the back of your paper that you have there, and at the bottom, right, I want you to be able to, if I just gave you just the picture with nothing on it, right? I want you to be able to tell me that relationship between the mean and the median. Remember, when it is skewed left, I have more data, or I have not more data. I have data that is smaller, right? It's getting smaller and smaller and smaller. And so it pulls the average smaller. This example over here was our football. Okay, so I have values over here that are going to be pulling the average larger. So the mean is going to follow the tail. All right, the median is more in the hump, we would call it. Okay. Okay. All right. Now there's 2 more questions on your paper there. I want you to see if you can answer those questions for me. And then we'll talk about the answers to those questions in just a second. So looking at question 2, FICO scores. So it says there that scores range from 30 to 850. Distribution is skewed left with a median score of 723. Do you think that the mean then would be greater than, less than, or equal to 723?
Last one is extreme low number.
That's right, it's gonna be less because the mean would have to be less than the median, right? Okay, so it would be skewed left like we said. Okay, what proportion of the individuals have a FICO score above 723? Yeah, it's a trick question, right? It feels like a trick question. Okay, if the median is 723, right? That's the middle of your data set, then 50% have to have more than 723. It feels like it's a trick, doesn't it? Okay, it's hard to get that median thing down. If we can get the number, we have to remember what the median really means, that half of the scores are that. All right, let's look at the next question. We want to determine which of the measures of central tendency would be most appropriate. Average home prices would be what?
Median.
Why?
So that you kind of rule out the extreme lows and highs.
Yeah, right. It's easily skewed, right? Our mean is not resistant. That's the word we're going to be looking for. The mean is not resistant to large or small numbers, to very large or very small numbers. The mean is not resistant. It is easily influenced by those values. The next one says the most popular major for students enrolled in a statistics course. Which one would we use there? What was the key word in that? Oh, all right. Average test score when the scores are distributed symmetrically. The mean and why?
Because it doesn't, sorry, nothing's gonna hold it.
Because it says that they were distributed symmetrically, right? So it would already be symmetric. Then it is the thing we would look at. How about the average test scores when they're skewed right? The median, right? Because again, the median is not influenced, right? I just graded my pre-calc classes test, okay? I can look at the average and then I can look at the median. For my class, the median was the most appropriate way for me to look at it because I had several grades that were low, that were very low, and they just pull that data, right? They'll pull that average down, and yet really, I had 50% scoring above a very nice value in that class. All right, average income of an adult between 50 and 54. Why do you think median?
Again, get away from those extremes. the positives.
Right, because you have, if you're talking about somebody who's 50 or 54, you have all sorts of income levels that you could have for someone of that age, right? All sorts of different incomes. And then most requested song on a radio station, as it said most, right? Okay, all right, so that is the measure of central tendency, okay? And when we are